Okay, welcome everybody to this evening session of the conference. And we have with us Professor David Huse from Princeton. And he will be talking to us online about quantum thermalization and many-body localization. The talk is for lecture is for 1.5 hours. So I'll give you some indication at 1 hour 20 minutes so that you know that some end is approaching. Is that okay with you, David?
Yeah, that's fine. And I like to have questions during, so I will pause for that.
Yeah, if you pause, we will have the mic go around, and if people have questions, we'll,
Yeah.
Yeah, okay. So over
okay.
to you. Yeah, thank you.
Go ahead.
Yeah, please go ahead.
Yeah, so so my topic, so this is a pedagogical lecture, so I'm going to begin with some basic stuff. Quantum thermalization, talk about at least some definitions. And then I'll talk about many-body localization, of which quantum thermalization is the opposite. So that's why these two go together. They're the two phases of systems of interest. I put my email over here. I know in this format, it's often hard to get good discussions or questions answered. So if you have more questions that haven't been addressed, get in touch. Okay, so we'll talk about strictly closed quantum many-body systems. Excuse me. So I've drawn a little box here with stuff around it, inside of which I have n degrees of freedom. They might be qubits, they might be ultra-cold atoms, or they might be any quantum degrees of freedom. And I have a Hamiltonian of how they interact with each other inside that isolated system. And so the dynamics is just Schrödinger's equation given by that Hamiltonian. Okay. So we have a quantum many-body system that's fully isolated from any environment. And of course, this is an idealization. Laboratories are trying to approximate this as best as they can. But as theorists, we can think about this idealization. And that's what I'm going to talk about. Now, what we're interested in is systems that are initialized in some non-thermal initial state that's not in thermal equilibrium. And I'll call that rho of t equals 0. In general, the initial state will be a density matrix. You can also think about pure states, which also are an idealization. In laboratories, people strive towards making pure states, but if in a many-body system, you really can't because they just don't have that degree of control. It's always a mixed state. Okay, now we're just going to talk about the dynamics. This is just basic stuff. We're just going to talk about the dynamics due to this Hamiltonian. And that is simply this, very simple, superficially simple, right? Just this evolution. But enormous complexity is hidden in here because H in general has a very complicated spectrum and very complicated eigenstates. And so this is not, although you can just write it here in this simple formula, it's not necessarily very useful in many cases. It's correct, but not something you can actually calculate. Okay, so what is thermalization? So on initially a little bit informal level, and I'll get a little more precise later, although I won't be fully rigorous. Thermalization means the system is a bath for its subsystems. So this system here, we don't have an external bath, but the system can be the bath if it thermalizes. And if it thermalizes, all small subsystems go to thermal equilibrium with each other. but in order for this to be a sharply defined thing, we have to take the limit of a large system and a long time. And I'll say more about that later. Okay, so first, for simplicity, let's assume the Hamiltonian is the only extensive conserved quantity, so we don't have to worry about, what does thermal equilibrium mean, right? If there's only one conserved quantity, namely the Hamiltonian, thermal equilibrium is given by a temperature or an energy density, right? And if there's no other extensive conserved quantities, the thermodynamics doesn't have any other parameters. Of course, there's the system n, but n, I'm assuming n is fixed, right? Okay, so now we have to be taking a large system limit, and let's say whatever the system is, as we take the large system limit, it remains statistically spatially uniform. The Hamiltonian remains statistically spatially uniform. When we talk about NBL, we're going to have random terms in the Hamiltonian, but they're going to be drawn from the same probability distribution everywhere. So although the system isn't strictly translationally invariant in uniform, it's statistically spatially uniform, right? So that makes the large system limit something that's reasonably nice to deal with. Now, in order to thermalize in this limit to a definite temperature, you need the initial state. Since energy is conserved, because we have a Hamiltonian, you need the initial state to be such that the energy has a probability distribution in the large n limit, which corresponds to a particular temperature. And that means you need the system to have some given energy density in its initial state in the limit of large systems. So we're going to take a limit, and in the limit, our initial states have to satisfy this, that they have a definite energy density. The variance of the energy density goes to 0. So then the variance of the temperature will go to 0, and we can thermalize to a particular temperature. Right? So we're going to put this one restriction on our initial states. And this isn't unnatural. Any simple way of preparing initial states in the laboratory will, by the central limit theorem, you'll just, the total energy will just be a sum of random terms, and the central limit theorem will make this true. So it's not a unphysical thing to ask for. In fact, it's hard to violate this in the laboratory. But just I'm going to say, I'm going to make a definition of thermalization such that all initial states will thermalize. And when I say all initial states, I mean all initial states satisfying this. Okay, so now I'm going to erase any questions. Say while I'm erasing.
Any questions, and we can take it up. I don't see any questions. I don't see any raised hands, David.
Whoops, there goes my system. I meant to keep it on the board, but. Okay, so to make this a little bit more sharply defined, when we ask, we want to ask, does the system thermalize or does it fail to thermalize? So really we need a series of systems and initial states, and then we take n to infinity, and also time to infinity as we do that. So to make thermalization really a sharply defined question, it isn't just about one system of a given size, it's about a series of systems as we take the large system limit. Okay, and so we want for all initial states, actually, let me just say all such, sorry, let me back up a bit here. So I'm going to give a fairly strong, there are various, people use different definitions of thermalization, but I'm going to use a particular definition, which is a reasonably strong one, which goes this way: for all initial states, and I don't mean almost all here, I want something where it's all initial states, but all initial states that do have, in the limit of large N, a well-defined energy density and therefore a temperature. And in particular, we're interested in non-equilibrium or non-thermal initial states. We want the limit n to infinity and p to infinity of rho of t is a thermal state. And now you have to take these limits, right, is a thermal state here at almost all times. Now you can always make initial states that will have some echo and go out of thermal equilibrium at any particular time you choose if you have precise control. So we can't ask it to be thermal at all times. We ask it to be thermal at almost all times. That way we don't have to worry about these, what are classically called Poincare recurrences, the quantum version of that. And then you also have to take the time to infinity fast enough compared to n to infinity in order to allow transport across your system, right? If you take n to infinity first, the transport time across your system will be infinite, and the system won't be able to thermalize, right? So one has to be a little bit restrictive on how you take these limits, but it's a pretty minor restriction. It's really just to allow transport. Okay. If there is transport, right? Of course, if we have a Hamiltonian, which we do right now, there will be transport of energy. Okay. And then, right now, okay, and I'm going to define later what I mean by a thermal state. This sounds maybe content-free, but I have to define what I mean by a thermal state. Right, what's I going to say? Right. First, I want to make one important point. So this is about dynamics. Does the system under its dynamics bring itself to thermal equilibrium? And it's not about thermodynamics. So when we have a phase transition, say between a thermal phase where it does thermalize and a many-body localized phase where it doesn't thermalize, that's not a thermodynamic phase transition. That's just a transition in the dynamics. So it's not about the thermodynamics. So the n to infinity limit doesn't have to be the usual thermodynamic. And in fact, for many, many systems that do or do not thermalize and have transitions between thermalizing and not thermalizing, say integrability or near integrability versus thermalization, MBL versus thermalization, or in flow case systems, say heating or not heating, you have all these transitions, which are dynamic transitions. And in many cases, to see them, you don't take the thermodynamic limit, you take different limits. And I'll give one example of that in a little bit. But it's a very important point that one should, in these discussions, one should not only look at the thermodynamic limit, because the thermodynamic limit might be uninteresting for these questions. A lot of systems do thermalize in the thermodynamic limit, but if you take the large system limit other ways, you get interesting behavior. Okay, so that's one point. Right, and in the context of NBL, there's a nice summary of the situation with this. There's this paper, Kolkata and Merlin, ERB 2018, where they talk about what are the appropriate ways to take the large N limit to study the NBL phase transition in many different examples. And we did some more in a paper with Sarangopalakrishnan. And then in the context of flow case systems, I'm just going to mention that we have a paper just recently, Ringstar itself and Money, same journal, 2023. So this is about flow case systems. Transitions between heating and non-heating in non-standard large system limits. And I'll give an example soon about that. Okay, so but first we want to ask, what is a thermal state? We say a system is a thermal state. What do we mean? Okay, so now in order to define this, we need to define subsystems. So we have, so an important point about many-body systems is they are consisting of many degrees of freedom. And in order to discuss whether or not the state is thermal or not, you need to first agree on what are your degrees of freedom, right? When you take your Hilbert space of your full system, and it's typically a product state over all degrees of freedom, you have to privilege those degrees of freedom. So you have degrees of freedom, and thus you have subsystems. And so right, and a subsystem is some subset of the degrees of freedom. And so let's say A is a small subsystem of our full system. And so it's got, let's say, NA degrees of freedom, NA qubits. And this is a finite, small, actually, let me just say finite subsystem. Okay, and B is all other degrees of freedom. And so when we ask, are we in a thermal state, and we ask about subsystem A, we look at subsystem A and ask, is B a good bath for A? And then we do that for every finite subsystem. That's basically how one defines the thermal state. Now, I'm going to erase here. Top. Right, of course. So with this situation here, and I have state rho of t, so the state of A is, of course, rho A of T is trace over B of the state of the full system. So this is the state of the full system. We take the trace over B, and that's the state of A. And the thermal state in this case where we have a conserved Hamiltonian has a temperature T, which is 1 over beta, 1. And for all finite subsystems A, the limit n to infinity, t to infinity. Well, not n, I'm just talking about the state, so I don't have to take t to infinity. I'm just asking for a particular state. OA of t T is rho A thermal of beta, which is the trace over B of the Gibbs distribution. Minus beta H, which is H beta. So certainly one thermal state is the Gibbs distribution. And if we take the trace on B of the Gibbs distribution, that's the equilibrium state of A. And that's what I mean here. So it's a definition, thermal equilibrium at temperature, inverse temperature beta, subsystem A. And a thermal state has the property that for all finite subsystems, the state of the subsystem is the thermal state at that temperature. Okay. So that's what I mean by a thermal state. And this, of course, includes all standard stat-mech ensembles. When you say two statistical mechanics ensembles are equivalent, what you mean is basically this, that they all have the same states on all subsystems. Right? But
David, there's a question.
Really exponentially many other states. And in fact, almost all states are thermal.
Hello? I have a question.
This is what's called quantum typicality. Von Neumann proves something like that in the many-body limit. Almost all states are thermal, but of course there are a lot of states of interest which are readily produced, which are out of thermal equilibrium and are not thermal.
David, can you hear us?
Yes.
Arijit has a question.
Yes, please.
Yeah, so this density matrix, is there a way to define thermalization? I mean, if you think of the subsystem, the trajectory of the subsystem, I mean, it's a mixed state, but we could also be thinking of the trajectory of A. Would the thermalization be visible in the trajectory?
Well, I want thermalization at a particular time. So on a trajectory, if you're talking about a trajectory, meaning you're making measurements, I'm not sure what you mean by a trajectory, but if you mean it in the usual way, that you're actually measuring things and following a quantum trajectory, that's never in thermal equilibrium by my present definition, right? Because at any time you've made a measurement recently, and you've recorded that data and it's out of equilibrium because it remembers, it hasn't relaxed away from that particular measurement, right? So a trajectory would be at equilibrium only statistically, an ensemble of trajectories or the long time average of a trajectory. But at any one instant of time on one trajectory, you're not in thermal equilibrium.
Okay. So
this is it's a particular definition of thermal equilibrium I'm using, right? Where I want the system. It's a stronger sense of being thermal than you have classically. In that, a quantum system, it can be, because of entanglement, it can be at thermal equilibrium in one state at one time, no averaging needed, right? Whereas you take a many-body classical system, in a particular state, you look at long times, it might go to thermal equilibrium in the usual sense, but if you ask at one particular time, every degree of freedom has a particular value. Right? And so it's not at thermal equilibrium. Thermal equilibrium is a distribution, right? But quantum systems, they thermalize in a stronger sense than classical systems. So, I'm not saying this is the best definition of thermalization. I'm just saying it's a definition I'm going to use, and I like it. But there are definitely other definitions of thermalization, which in some sense are weaker. Right, because this is really asking for a lot, right? I'm asking for all initial states, all subsystems, thermal equilibrium at a given time, no averaging over trajectories, no averaging over time. So it's a very strong definition. It's really asking a lot, and classical systems just never do it for pure initial states. But quantum systems do when they thermalize, right? And that's why I like this definition, because in some sense it's the strongest one, which is consistent with what we see in terms of the behavior of quantum many-body systems that do thermalize. See what I mean?
Yeah. Got it. Thanks.
Yeah. There's another question.
Yeah, go ahead.
Hello. So when you say that this is the definition for your thermalization, do you mean a particular kind of interactions that you consider in the Hamiltonian, or do you say that this is true for any kind of interaction? The question I have specifically in my mind.
It's a question, right? I have a given system with a given Hamiltonian and a given way in the limit.
But is it true for long-range interaction in your Hamiltonian?
There are certainly many Hamiltonians with long-range interactions that do thermalize. Yes, they generally do. Okay.
Okay.
But yeah, not all systems thermalize, right? It seems like most systems, it's the generic behavior, most systems do, but it depends on the Hamiltonian.
So one last question from me, David. In your definition of what is the thermal state, you have taken the full thermal density matrix and traced over B. You have not really made a statement in terms of things only in A, like, whether it's like.
This is it only in A. Oh yeah, right. Okay, so there's another thing that's often said, which is thermal equilibrium of A. People write this, the thermal state of A is e to the minus beta HA, the Hamiltonian on subsystem A.
Yeah, I was wondering, that's not the one that you are using. Yeah.
Right, well, this is wrong, right? Because A interacts strongly with B, and this is ignoring the interaction Hamiltonian between A and B, right? And so this is only correct in the limit where the interactions between A and B are taken to 0. Okay. And that's a very special situation, right? And if I want it to be, right, if I want this to be true for all systems A, and all systems A interact arbitrarily weakly with their counterparts, I don't have a system that thermalizes, right? So this is basically only in very special circumstances where you have a subsystem that's very weakly coupled to the rest of the system, right? And then that subsystem is very special. Whereas I'm talking about general systems. My finite subsystem could be 1 qubit, and its Hamiltonian HA might be nothing, right? There might be no field on it, and it's interacting with other qubits, right? And so this is just generally completely wrong.
Wrong. Okay. No, I just want to make sure that that's what you're. Yeah. Okay. Fine. Thank you.
Right. We want to do a general case. In a general case, subsystem A is interacting strongly with subsystem B. Okay. Okay, now if this is true, okay, so for systems that do thermalize, by this strong definition, all eigenstates of H are thermal. Because of course, an eigenstate of H is a permissible initial state, right? It has zero variance of its energy, so it's a permissible initial state. It has no dynamics. And so if the system thermalizes for all initial states, then if I started in an eigenstate, it must go to a thermal state, but the state doesn't change. So the eigenstate itself must be a thermal state, right? And so this says ETH, the eigenstate thermalization hypothesis. So any system that thermalizes, thermalization is a dynamical question, but any system that thermalizes in the strong sense that I'm talking about here obeys the eigenstate thermalization hypothesis. So all eigenstates are thermal. And then, as I said, most, not all, of course not all, systems well, we don't know this, nobody can prove this, but the generic behavior, and when one tests it as best as you can with modern methods, numerical and experimental, we find that most systems do thermalize. The exceptions are require something special. And that's what I want to get to next, is saying a little bit about exceptions, and then focus on one particular exception, which is many-body localization. But maybe I'll pause again. So that's my sort of summary of defining thermalization and some of the issues about it, that if you want to make it strong, you need to put in, if it's strong and sharply defined, you need to have a series of systems. You need to take the large system limit. You need to only consider initial states with a definite energy density. Those are the points I wanted to make. Any other questions?
Sorry, can you hear me?
Yeah.
So you said that this condition needs to hold at almost all times. I was wondering, like, if you had a more precise notion of like how often it should hold, or what do you really mean, like measure zero where it doesn't hold?
Yeah,
or...
measure zero. Measure zero. Yeah.
Is that going to be true at any finite n?
No, it's in the limit.
But even in the
At
limit,
any finite n, thermalization is not sharply defined.
but I think that like
you have to take the limit.
But at any finite n, presumably there's like an infinite measure of times on which, like in like Lebesgue measure, at which this condition does not hold, right? But even if I just say that there's like Poincare occurrences which have some finite but small time, but there's infinitely many of them, then it, like, I don't know how to understand what you mean by like measure zero in the limit of n to infinity.
Well, I guess one way is you would look over a very long trajectory and look at the probability distribution of rho A of t, and you would see that collapses in the large N limit to a delta function distribution, arbitrarily sharp distribution with almost all weight arbitrarily close to the thermal state. And the part of the distribution of this that remains away from this goes to zero, right? And those are the special times where it's doing something.
I see.
Something
So
like-
it
something
requires
like
a limiting
something
procedure
like a
both.
spin or something.
Yeah, so it requires a limiting procedure both in N and in like the observation time. Have I understood that right?
You have to take both large N and large time. The system only thermalizes in a sharply defined way if you take both those limits.
Right. But I think the point that I was trying to like check is that it's not just that it's like an instantaneous time that you're taking to infinity. You're saying there's some like a window of time, and within that time you need this condition to hold like in the limit that window approaches infinity.
I'm taking the time to infinity and N to infinity, the time to infinity, enough faster than N so that transport can happen. And then I'm saying for almost all such times I choose where I take the limit that way, I will get this result.
Okay, I think, yeah, okay, I understand. You're taking it like N and T to infinity simultaneously with T growing with N. And
Yeah.
you're saying like, yeah, okay, I understand. Thank you.
David, there's a question.
I do want that at a typical time, it thermalizes, right? I don't want to have to average over time. Go ahead.
There's one question in the chat. It's from Nilotpal. He says, is there an understanding or some toy model as to why most systems thermalize? Is there a simple way to understand why most systems thermalize, or some toy model way of understanding that?
Yeah, No, I wouldn't say that. When I first started talking about MBL and, we got a one-dimensional quantum system with random fields, people, because they knew that single particles in one dimension and random potentials were always localized, you would think, oh, one-dimensional systems with random Hamiltonians would always be localized, because it's true for the single particle problem, right? And so people would say, oh, why do you ever thermalize? So it's not simple, no. But and it's the kind of thing that's way beyond what anybody can prove. But there's a lot of systems that have been looked at very thoroughly in numerics, and you look at the trend with system size, and it's trending towards thermalization very clearly and very strongly, right? So now there's really no doubt about it for lots of systems, but I think it's only because of very good numerics that's been done. So in that sense, I don't think it's simple.
David, can you hear me?
Yeah.
So when you state that all eigenstates of H should be thermal from ETH, are you excluding the ground state and low-lying excitations, or?
The ground state is thermal.
So
the ground state is thermal, right? If the ground state is unique, it's thermal. Because how could it not be thermal, right? There's only one state at that energy. So thermal equilibrium is the ground state, in the ground state, at zero temperature. So it's really, now there's some subtleties near zero temperature that the deviations from being thermal, you have to take large N in some, the size N you have to go to in order to see that all states are thermal at low temperatures diverges as the temperature goes to zero if you're at non-zero temperature. So there's some subtleties there near zero temperature, but I think we believe that for generic systems, this would be true at all temperatures, including zero temperature. You know, zero temperature is actually simple, because if you have a system with a unique ground state, it's automatically thermal even for finite N already.
Can you hear me?
Yeah.
Okay. So according to ETH, I think there exists more than one thermal state for any system. Is it?
Yeah, like I say, almost all states are thermal.
No, but
almost every state is thermal.
no, but the question is that do you have some understanding, or like can we figure out something about the system based on which thermal state it is going to, or it will, like we have a Hamiltonian and then
Well, generally, you know, if the system, or if we have a large system and it goes to thermal equilibrium, it basically means it's hidden, right? So right, if we consider all finite subsystems and they're all at thermal equilibrium, everything we could measure about the system is a property of a subsystem, because we can only measure things that involve some finite number of degrees of freedom.
Mhm.
So if the system goes to thermal equilibrium, goes to a thermal state, it means all information about the initial state is hidden from you. You can't measure it. It's gone to operators that are too hard to measure, too many degrees of freedom to measure. So that's why you have an enormous number of thermal states, but they only differ in things which are not observable, right? And that's, and you know, each initial state will go to a particular thermal state at long times, but those thermal states are all indistinguishable from each other because their differences are only in terms of operators that are just non-observable because they involve an infinite number of degrees of freedom.
okay, yeah, thank you.
So I think asking about, you know, which thermal state are we in, you know, this is in some sense, you know, it's something which you can't do in the lab, right?
Yeah.
And so, you know, we can talk about it, but I don't know that we should focus on it.
Hi, David. And so I have a question which similar to what Arnab asked. I mean, so if you look at the zero temperature, I mean, then it's the ground state, but then the reduced density matrix might show area law, right, for the entropy.
Yeah.
But the right-hand side, the thermodynamic here should be volume law, right? That's just the ground energy
No,
of
no,
the...
not in the ground state. The ground state, right, you just put in the ground state here. The ground state here, this is just one state.
But the energy should be, that's like the energy should be extensive, right?
Yeah, the ground state has an extensive energy, typically.
But the left-hand side, the entropy, that would give you a...
Entropy is zero.
Okay.
The ground state has area law.
Okay.
The thermal state has area law in the ground state.
Right, okay.
I'm not saying anything sophisticated. It's actually, you know, there's only one state over here. And so therefore, you know, there's only one, at zero temperature, if we have a unique ground state, there is only one thermal state. And the thermal state is the ground state, right? And it's just sort of trivial.
A slightly complementary question to the previous one. So do you want to exclude cases where almost all eigenstates thermalize, but there are like some exceptions in this definition?
Well, okay, so what I want to talk about next is exceptions to thermalization. So that's where I'm going. So I'll say a little bit about that. So I will mention those cases, but then I will move on past them. Yeah, so shall I go on?
Yeah, then there are no more questions. Thanks.
Yeah. Exceptions to thermalization. Now, as was just asked, there are scars, many body scars. And this is where, you know, some eigenstates are not thermal. But as far as I understand, with many-body scars, almost all eigenstates are thermal in the limit of a large system. So this is one case of systems that don't thermalize, which was discovered fairly recently and has received a lot of attention. And I'm sure you're having talks about them at this meeting. I'm just mentioning it, but I'm not going to talk about it at all. Okay, so that's one case. There's fragmentation. Which I'll not write anything about it, but it's basically when you have a Hamiltonian, which has got a lot of matrix elements that are zero. So the Krylov spaces of the Hamiltonian break up in a way which isn't just due to traditional conservation laws. It's due to more microscopic details. And that's, again, something that's receiving a lot of attention, and I'm sure you have talks about that. So that's another case of systems that, so these are both, as far as I know, fine-tuned. The scars are, as far as I know, are not robust to small perturbations to H. And the fragmentation is always due to zero matrix elements. As soon as you make a lot of those matrix elements, as soon as you start making those matrix elements just small, but not zero, just make them very small, the fragmentation is gone. So these are both exceptions to thermalization that, as far as we understand, are not robust to generic perturbations to the Hamiltonian. And then the one I'm going to talk about is NBL. So this I will discuss. Okay, and then there's another one we could have. So let me just say this here. So we could have more extensive conservation laws. Say we might have a Heisenberg model and we have conserved total spin as an example. So this is an example. And then we are, so then we have, you know, more parameters in the thermal state than beta, right? So if the only extensive conservation law is the energy, the only thermodynamic parameter setting the thermal state is beta. But for every conservation law, you need another thermodynamic parameter defining your thermal state, because that quantity, you know, has some density. And then the other exception, well, it's not really an exception to thermalization, but it's sort of a generalization of thermalization, is integrability. The cases of integrability where you have, in the limit of a large system, an infinite number of conservation laws, so number of conservation laws goes to infinity as n goes to infinity. And then you have a thermalization which is generalized. Yeah, let me just call that generalized thermalization. Thermalized to a generalized Gibbs ensemble, which has an infinite number of thermodynamic parameters. And I just wanted to mention that as another case of thermalization, but I'm not gonna say anything about that type of integrable systems. Although you can view MBL as a type of integrability, as I'll say, but it's a different type of integrability than sort of more traditional integrability like beta unsolvable systems, things like that. Okay. So this is just some comments about exceptions. Now, integrability is also not robust generally. So in some sense, all these things are not robust. The MBL has a certain degree of robustness to certain types of perturbations, as I'll mention. Okay, so what I'm going to do now is go to talking about many-body localization. So I'll pause again, see if there's more questions. Is that a race? Localization is the following. Okay, so we have n qubits, spin 1/2, and we have an Ising Hamiltonian. So that's this, h equals 1 to n, some field on the coupled to the z component of that spin, and some interactions, and I'll just put 2 spin interactions. So we're viewing this not at, it's an Ising Hamiltonian, but we're not viewing it as a statistical mechanical problem. We're viewing it as a quantum Hamiltonian, which is giving the dynamics of the system, right? And because the Hamiltonian has no spin flip terms, every single one of these spin operators is conserved. And so what we have is an extensive and complete set of localized conserved operators, namely the ZIs. They commute with each other, ZI J, and commute with the Hamiltonian. So this is, in some sense, the prototype or the fixed point of a many-body localized system. Now, of course, we could have higher order terms, more ZZZ, ZZZ, etc. Okay, now one comment about this. So let's say these are just random fields and random couplings, and they're drawn from some distribution with a width of order 1. So that's our Hamiltonian. So this has energy level spacing. Okay, so now when we talk about many-body localization, we're not talking about low energies. So we're talking about high energy states, typical states that would correspond to infinite temperature for this Hamiltonian. So near energy 0, right? And there, almost all states in this Hilbert space are near infinite temperature, and there are exponentially many of them. So it has energy level spacing 2 to the minus n. So the level spacing of this system at the energy range we're focused on, which is going to be high temperatures, typical states, is this, and it's 2 to the minus n. It's exponentially small in n. So it's extremely gapless. Usually when we say a phase, in a lot of discussions of, oh, we have a critical phase and it's gapless, what we mean is the gaps are power law small in the size of the system. Whereas here, they're not power law small in the size of the system, they're exponentially small in the size of the system. So that's what I mean by extremely gapless. Right? And so because of this, the MBL phase is a critical phase. In a strong sense, it's critical, it's gapless, it's full of level crossings. And that's an important point I want to emphasize. Okay. Okay, so this is trivial. You might think it's trivial, but this is, as far as we know, the structure of the MBL phase. So more generally, MBL phase has this structure with conserved localized operators. I call them L bits. Tau I, and the tau i's are Zi plus multi-spin terms these K in space. So now these are localized. This L means localized conserved operators. And then the Hamiltonian looks like this with taus substituted for the z's. They interact with each other, but they're all conserved. And each tau I, when we write it in terms of the microscopic degrees of freedom, is localized near one of them with tails falling off as you go away. Now you might think this is a perturbation on this that we could just calculate perturbatively, but that's not true because the phase we're working in is a critical phase. And so one can't just simply do perturbation theory. As you move through the MBL phase, everything is highly non-adiabatic, and so you can't just perturbatively do that. So these are in some sense non-perturbative. They're small, but non-perturbative. And again, that's an important point, that these, as you move through the MBL phase by changing parameters, these tau i's do not evolve adiabatically because you have all of these level spacings and you're constantly doing weakly avoided level crossings, which are producing singularities. So the MBL phase, and that's the sense in which the MBL phase is a critical phase. And if you want to do anything perturbatively within the MBL phase, you have to take extreme care because it's a very dangerous place to do things perturbatively. And I think you'll hear more about that next week in John Embry's lectures.
Can I?
Where he's doing that. Okay, and I'll next go to a particular example to talk about that a little more. But yeah, go ahead.
Can I maybe
Yeah.
object a bit? I don't want to start a long discussion about MBL, but I kind of strongly object to calling the system integrable. I think
Oh, that's just semantics.
Yeah, I don't think the eyes exist really. So in a
Yeah,
sense
well,
that
I'm aware of that.
yeah, but in a sense, can I?
Let's save that until we
Okay.
have talked about MBL.
Yeah, what I want to mention is that if you take normal systems, which say classical, which KM systems, right? They first become chaotic and only much later, if ever, they become ergodic. When they become chaotic, there are no new integrals of motion. You just cannot take average radius of the orbit, time average, which is finite, and call it integral of motion. So, and something similar happens to MBL. So absence of adiabaticity actually means that Zi is not just non-analytic function. It's not a function at all, it doesn't exist. It's not a function of L, of disorder, or whatever. It's kind of fine-tuned to your specific eigenstates. So it's kind of like projection operator. So projection operator is not a function. So it will have regular part. So it's true that you have almost conserved the eyes, that's for sure, even in localized phase. But there is also irregular part, which is like as sensitive as eigenstates, say.
Yeah.
But then we shouldn't call it integrable, I would say.
Well, I think if the Hamiltonian can be written this way with tau I, tau j, tau I, tau j, tau k, if the Hamiltonian can be written that way, we have a complete set of conserved quantities. It's a type of integrability. It's a very different type of integrability than all the other ones people know about, right?
Oh, but any Hamiltonian.
But it's a term that, you know, we can. It's fine to say no. I don't want to call that integrability. Let's call it something else. But I think it's a type. I find it to be a type of integrability. But it's a special type, right? And certainly one could say, no, that we don't want to call it that. We call it something else. And I'm fine with that. But that's just semantics. Okay, so I want to.
Can I have another question before?
Okay, go ahead.
This was localized because HI was disordered, or because you had infinite integrals of motion? It was every term was commuting with the Hamiltonian. HI was disordered or not?
Well, in that case, it's not important that it's disordered because the Hamiltonian just explicitly has those integrals, those conserved quantities. But in order to have any robustness, you know, you want, right? So, so we're gonna actually let me write down. Let me just add a term to the Hamiltonian to make it less trivial first. Okay. So less trivial. I'm gonna do a case. Add some spin flip terms to that Hamiltonian. Okay, so here I'm following, although I've highly distorted what they've done, Altshuler, Geffen, and then F, Levitov. So this is the paper that started the modern study of many-body localization, PRL 1997. So what I'm going to tell you now is a highly distorted version of that, and it's something we discussed. So we have a recent paper, Chandani. I think. Yeah. So a less trivial example. So same Hamiltonian. Sum over I, n qubits, HI, ZI. And now in order to make the field term and the interaction term the same scale, I put a 1 over square root of n here. Okay. And then I'm going to put a transverse field to put in a spin flip term. So now I put in a spin flip term with transverse field gamma. And as I take my limit of large N, I'm going to allow myself to vary gamma in order to see the MBL phase. Because this is a model where if I take the standard thermodynamic limit, it thermalizes and you don't see the MBL phase. Okay, so now, right, if we're going to add the spin flips and look at the stability of MBL to that, we want this part of the Hamiltonian to be such that it doesn't have a lot of degeneracies. So we either want randomness in these fields and these couplings, or we want something like quasi-periodicity or something like that in order to have the spectrum of this thing before I put on the transverse field not have a lot of degeneracies. Right? Doesn't have to be disorder. It could just be some non-random but non-translationally invariant pattern of these fields and interactions, like quasi-periodicity is an example that people study a lot. They don't want randomness, but they don't want the degeneracies either. Okay, so this is the Hamiltonian I want to talk about, right? And so let's just say, you know, Hi and Jij have mean 0, variance 1. So say they're drawn from Gaussians. And we're gonna look at a typical state of this. So therefore T temperature is infinite. Now this, as many of you know, this is the Sharon-Kirkpatrick spin glass, Ising spin glass, which we know has a spin glass phase, but that spin glass phase is nowhere near temperature infinity, right? And so although this model in a completely different part of its phase diagram has a spin glass phase, I'm very far away from it. And so this isn't spin glass physics, right? We're talking about spin glass at extremely high temperatures where it far from the spin glass phase, okay? And we're asking about its dynamics, okay? Okay, now, as I said, we want to ask, you know, does this system thermalize? And that means we have to take a large N limit. And so we're going to allow gamma N to go to 0 as N goes to infinity, because that is the scale in order to see the transition between many-body localization and thermalization, okay? And the relevant scaling which was obtained, well, actually, say a little bit about that later, is gamma then going as 1 over n log n. Now, in this case, so this case, this is the case of what's called Fock space localization. Which is what Altschuler and company introduced. So if we first turn the transverse field off, the eigenstates of this are just spin up, spin down. So the Fock states are the eigenstates of the complete set of Z's. And then this X, and this is these are the corners of a n-dimensional hypercube. I just take all that take that full Fock space, it's the corners of an n-dimensional hypercube, and then the xi gives hopping on that hypercube. Nearest neighbor hopping along the edges of the hypercube, you flip one spin. So the hypercube is, each direction on the hypercube, one side of the hypercube is spin up, the other side is spin down, right? And along each of the n directions for the n spins, and then the xi flips one spin, so you hop from one corner of the hypercube to the opposite side along that direction, which is a nearest neighbor hop, right? So, I can only draw 3 dimensions, and so this would be one particular spin pattern, and this one, if I hop from here to here, I flip one spin. If I flip another spin, I go this way, another spin, I go this way, and there's n different directions. Okay. Now, what happens here, so why does the transverse field, in order to see the many-body localization, why do we have to take it to 0 as 1 over n? So each state has n neighbors. So if I take one spin pattern, up, down, up, up, right? The transverse field can flip any of these spins. So the Hamiltonian will give a hopping to flip this spin, or so there's n neighbors that it can hop to. Since I've chosen all these terms of variance 1 and put this 1 over square root of n here, the change in energy of the diagonal part of the Hamiltonian is going to be order 1, but random, if I have these guys random. And so I have n neighbors with delta E of order 1, and so the minimum, the typical minimum is of order 1 over n, right? If I have an interval of length 1 and I put down n centered on 0, and I put down n particles, n points at random, the closest one to the origin will be a distance 1 over n. And so one of these spin flips will cause an energy difference that's order 1 over n. And then if the transverse field is bigger than that, those two states will hybridize strongly in the eigenstates, and that means these particles are hopping rather freely on this cube, right? And so in order to localize, in order to make it so that this hybridization doesn't happen, right? So I've got my given state here. There are the n neighbors, n neighboring states under spin flips, spread out over an energy interval. This is energy this way, energy interval of order 1. The closest one is that energy difference 1 over n. And in order to not hybridize with that, I need my transverse field small compared to that. And so that sets the scale for where the transition happens. And so for gamma less than gamma c, and again, we have to take the limit, right? We take n to infinity. As we take n to infinity, gamma n behaves like this, and gamma c behaves like this. And if gamma is less than gamma c, we find the MBL phase, where we have Fock space localization. The eigenstates are localized near the corners of the particular corners of this hypercube. And then for gamma greater than gamma c, we have presumably thermalization. I think in this case, it's the MBL, which is more cleanly demonstrated, but because once the states can start hopping in this Fock space, showing that they actually thermalize is a non-trivial thing. But if you look at it numerically, it certainly looks consistent with that.
Is there a way to see why you need the log correction?
Sorry?
Is there a way to see why you need the log correction to gamma n?
Not a simple way. So actually, this is due to Abu Chakra, Alice Anderson. So this problem on a general random graph without loops. So the hypercube does have loops, but the loops are rare enough that they're not important. So Abhachakra, Thallis, Anderson considered this ignoring the loops, and we believe that's correct for this problem in the limit of large N. And this is J Phys C, 1973. And they obtain the log. So they basically have an exact solution of this problem, ignoring the loops. And the log is there. It's due to higher order terms, right? I'm just asked, when I say gamma, you can make a naive argument that gamma goes as 1 over n just due to the nearest neighbor hoppings. And that's correct up to the log. If you could do it more carefully and worry about the higher order processes where it hops, virtually through higher energy states, for many steps, and then goes back to on shell, you get this extra log that it sort of delocalizes more easily due to these higher order effects. But that's a hard thing to really show. So what I want, the reason I wanted to show this is like a simple example of MBL, and it's typical of MBL models above 1 dimension, or even in 1 dimension with longer range interactions, in that in order to see the MBL, you have to take a non-thermodynamic limit. So if we take the limit this way, this term is thermodynamically 0 in the limit. So it has no effect on the thermodynamics, and we get the thermodynamics of this Ising model, right? But it has an effect on the dynamics, right? So you can have terms that are thermodynamically completely irrelevant, but are dynamically completely relevant. And that's why you have to take, in many cases, in order to study the interesting transitions in the dynamics, you need to take large system limits that are different than the thermodynamic limit.
I have a question.
This is one of the simple examples where, in order to see MBL here, that's what you have to do.
David, can I ask a question?
Yeah.
Is there some possibility to add p-spin terms to this, since like a mixture?
Certainly, I think as long as it's a finite number of, as long as the number of couplings is, the number of spins in the interaction term is small, I don't think the story is going to change much at all. Right, of course, in Altschuler and company, it was like this, but then this was a 4-spin term because they were doing electrons, and so, it was a scattering term where 2 electrons scattered out of 2 orbitals into 2 other orbitals, which translates to flipping 4 spins, right?
Yeah.
But these, as far as we can tell, these are details, right? The general picture, right? What power of n you're going to get here will change, right?
Yeah. Is it possible to also get a mobility edge in this model by taking a different limit?
Well, I'm sure this model has mobility.
AGKL had.
Yeah,
right?
this model. I'm sure this model has mobility edges, just as I've written it. I haven't really worked it out, but I would be amazed if this model did not have mobility edges as I've written it. But I'm focusing at infinite temperature, right?
Yeah.
But, I'd be amazed if this model didn't have mobility edges.
I have one more question. Can I think of this as a weakly interacting model though? Because like the interaction strength seems to be thermodynamically relevant.
No, it's not weakly interacting because this is an interaction. And that sounds.
Okay.
Spin flip term is weak, but the interactions aren't weak. Okay, so that's just an example illustrating how a model, in order to see the MBL to thermalization transition in a fairly standard kind of model, you have to take a large N limit that's different than the thermodynamic limit. And that's, like I say, that's true quite generally, except in one case.
Sorry. Can I ask one more question?
Systems with very short range interactions, and that's what I'm going to spend the rest of my time on. Okay, somebody else had a...
Yeah, one question. So Fock space localization here is the same as MBL, or MBL includes Fock space localization?
I would say MBL includes Fock space localization.
Okay.
So systems with long range interactions generally are in the Fock space localization. You know, basically Fock space localization means there's a particular basis, you know, which you can go to Fock space, and then it becomes a particle hopping on that graph. And that's a correct picture of it, and you don't really have to worry about the loops. The loops don't have a strong effect, and you can apply this kind of analysis. And this is true with long-range interactions beyond a certain power law, which depends on the dimension. That's in this Tikhonov and Merlin paper, there's a real discussion of that. And also, actually, I should have mentioned, there's another, yeah, so I have a paper about with Sarang. So there's this Tikhonov and Merlin paper I mentioned earlier, and we extended it a bit further, this discussion of these non-standard, non-thermodynamic limits you have to take. And so we discussed this in this paper here. But the Fock space localization is generally long enough range interactions beyond, you know, they can decay with a power law if the power law is slow enough. And then you end up in the Fock space localization regime. But it's a subclass of many-body localization. I would put it that way. Okay, so the one case where you find, at least it appears you find, the MBL phase transition in the standard thermodynamic limit is 1D models with short enough range directions. And that's what I want to spend the rest of my time on. Now, and you know, usually when one talks about, oh, the interactions is short enough range, you say it's short, it's a power law, but it decays fast enough. And exponential is fine, right? But what happens in MBL, because they're so gapless, right? Instead of the gaps being power law in N, they're exponential in N. When we say short enough range interactions and hoppings, what we mean is exponentially decaying and decaying faster than some decay length, which is of order 1, right? So there's a very strict condition on how short range the interactions have to be in order to be really in the 1D short range regime of MBL. And so it's these cases are the one cases of where it appears that the MBL phase can survive in the standard thermodynamic limit. Okay, so what I'm going to look at now, and that'll be the rest of today and tomorrow for me, is the so-called standard model of MBL, which looks like this. It's a spin-a-half chain, qubit chain. I'm going to write it in not the standard way, but it is the standard model. I'm just using a slightly different parameterization. So the Hamiltonian, so it's a chain, and I'm gonna have open ends, because that's nice for some purposes. So it's of length L, have fields. So the HI are uniform in -1 to 1. And then plus J -1 to L -1 sigma. So we just put a Heisenberg interaction, no randomness in the interactions. So this sigma I is just the vector containing the Pauli operators. At each site, I labels the sites. And we're going to look at typical states, infinite temperature. So we've really just got this one parameter J. Now this is usually presented where the J is equal to 1, and then you vary the strength of this term. Whereas I've decided to set this term to 1 and vary the strength of this term. And I think that's more appropriate because the sort of prototypical MBL point in the phase diagram of this is J equals 0. And I don't want it off at infinity. I want it at J equals 0. So we just have two terms, and we just got one parameter, which is the relative strength of the two terms. Obviously, if J equals 0, this is MBL. And then we want to ask what happens when J is non-zero. And notice it's only nearest neighbor interactions. So no exponential decays, only nearest neighbor interactions. Okay. So this model has conserved Hamiltonian, of course, and it's also got conserved total Z. But as far as we know, the physics of MBL, these conservation laws are not important, all right? And so actually, in modern serious studies of MBL, we typically study Floquet models with no conservation laws because the conservation laws are just sort of extraneous physics, which is distracting for studies of MBL. But they don't seem to have large consequences. So, and this model has been highly studied. The reason it's the standard model is not because it's a good model, it's just because it's very highly studied, the most highly studied model. And people are familiar with it, and so I'm going to talk about it. I'm not saying it's the best model, but I'm doing it just because it's familiar. You know, it's just the Heisenberg chain with a random field along the Z direction. Okay. Yeah. Okay, so we're going to consider typical states, infinite temperature. So T equals infinity, and so therefore the energy is near zero, energy near zero, right in the middle of the spectrum. We're going to vary J, and we're particularly interested in J well below 1. If J is of order 1, this thermalizes very robustly. So the MBL physics is all at small j. So let me just say one thing. You know, MBL is quantum coherence. Thermalization is decoherence. The system is able to decohere its subsystems. And as we all know, in quantum mechanics, decoherence really has the upper hand on coherence. And so when there's a battle between decoherence and coherence, the decoherence almost always wins, right? And so that's why this term is enormously more powerful than this term, because this term is trying to make MBL, whereas this term is trying to thermalize. And so this term is doing something that's, in some sense, easy to do, and this is doing something that's very hard to do. And so that's why the balance between these two is when the parameter J is quite small, right? And so that's why I wanted to put the parameter here. So we have a small parameter. But I guess I'm out of time. I think that's, as you know, it's sort of set up what we're going to do, right? So we have the trivial limit where J is 0. That's MBL. And then we're going to ask what happens at small j and explore that phase diagram and the physics around there. And we'll do that tomorrow.
Okay, let's first thank David. We have had a few questions, but if there are any urgent ones, a few maybe. No questions? I think we had a lot of questions about this, so people have run out of steam on this. So thank you, David, and then we'll see you again tomorrow evening.
Yeah, looking forward to it. Morning for me. Tomorrow morning for me.
Tomorrow morning for you. Sorry, it's evening.
Yeah, no, that's fine. It's snowing here in Princeton. We had fresh snow last night.
Oh.
You probably don't have snow in Bangalore.
No, it's pretty hot. I mean, it's a bit chilly, but it's hot, essentially. Yeah.
Okay.
Okay, so let's thank David once more just to finish this up.